Okay, today I just wanted to revisit a problem I did about a week ago or a few days back. We have the integral of 0 to infinity, x squared over e to the x minus 1 dx. Okay, now I didn't really go back and watch the video I did on this, but I think I might have missed, I don't know if I made it clear that this is really the same thing as something else I did. I think this was from the UK integration B, where they just had the exponent as s minus 1. So this was the more general form where you could plug in basically anything for x. I don't remember the restrictions. I think s has to be greater than 0. I think there are some restrictions on s, but I don't remember exactly what. I mean, I know we're fine if s is greater than 0, I think. And in that video, we found a general formula for this integral. It was just gamma of s times the Riemann zeta function of s. So with this formula, you could just do this really quick because you just need to know what s is. So like in the case that we did before, when we had x squared, that's going to be our s value is going to be 3. If I write this as 3 minus 1, that's x squared over ex minus 1. And so then we just plug in the 3 here in our formula and we get gamma of 3 times Riemann zeta of 3. But we can write the gamma function in terms of factorials. Gamma of 3 is going to be the same thing as 2 factorial. So what we found in the previous video is this solution is just going to be 2 times the Riemann zeta function of 3. And I don't know if I've done this other problem. I feel like I did, but it's somehow I don't know where that video is. Anyway, if you just, instead of having x squared, if you just have x over ex minus 1. Yeah, I must have done this one. Maybe I just did it, maybe it was a while back. So then anyway, this is, for the exponent 1, we can write this as 2 minus 1, use our formula, gamma 2, Riemann zeta of 2. But this is even kind of nicer, I guess. I mean, nicer depending on your perspective, I suppose. But gamma of 2 is going to be just the same thing. Using this is just going to be 1 factorial, or 1. So let's just leave that off. This has a known value, whereas this we had to kind of calculate. This we know to be pi squared over 6. So for this one, we get just pi squared over 6. And so, of course, we could just do this all day. It would get less and less interesting. I mean, you could, if you want to do it for 47, do it for 47. But you'll get, if you do it for 47, you get 46 factorial. I have no idea what the Riemann zeta function of 47 is, but I'd probably just leave it that way and you could calculate it on Wolfram Alpha. Now, just one more thing on this before I finish up. Let me get a little space here. One thing we can do on this, or kind of a common way to look at this, is if you just divide, if we look at this as an equation and we just divide out the gamma function on both sides, then what we can do is isolate the Riemann zeta function and get an expression for that. So what you can do is write this. Riemann zeta of s. So what we can do to get an expression for this, we divide this off. We have 1 over gamma function of s just times this whole integral right here. Not sure how useful that is exactly, because then to get a value for the Riemann zeta function, you'd be calculating this integral. But either way, another way to look at it. Okay, there you go. Thanks everyone for watching today. Have a good day.